Welcome, everyone, to another session on Dr. Liu's VCE Physics channel. In this video, we'll be tackling light as a particle from the NHT 2024 physics examination. I'll be guiding you through the solutions and concepts, and I encourage all teachers, parents, and fellow students to contribute any insights or corrections you may have. Option A is correct. The higher work function for metal 2 means the incident photon's energy is used to a greater extent to overcome the binding forces in the metal, leaving less energy to be converted into the kinetic energy of the ejected electron. Therefore, the photoelectrons from metal 2 will have a lower maximum kinetic energy. The energy of a single photon is proportional to its frequency and is inversely proportional to its wavelength. We can use Planck's constant and the speed of light to calculate the energy of a single. Power is defined as energy per unit of time. In the case of a laser, the total energy is the energy of a single photon multiplied by the number of photons emitted in that time. So, the number of photons emitted per second can be calculated by dividing the total power of the laser by the energy of a single photon. We are experimenting to investigate the photoelectric effect by shining monochromatic light onto a calcium plate. The maximum kinetic energy of a photoelectron is equal to the work done by the stopping voltage, which can be expressed as, and its numerical value in electron volts is the same as the stopping voltage in volts. The work function represents the minimum energy needed to remove an electron from a solid. Using Einstein's photoelectric equation, the work function can be calculated by subtracting the maximum kinetic energy of the ejected electron from the energy of the incident photon. The photon's energy is determined by multiplying its frequency by Planck's constant. The maximum kinetic energy, which can be measured experimentally, has a numerical value in electron volts that is equal to the stopping voltage in volts. If you cut the light intensity in half, but keep the frequency the same, you'll get half the number of photoelectrons. This is because intensity is about how many photons you're sending. The stopping voltage, on the other hand, stays the same. That's because the stop voltage is tied to the kinetic energy of the fastest electrons, and that energy is only determined by the frequency of the light, which hasn't changed. When the photocurrent is always zero regardless of the applied voltage, it means the new light frequency is below the threshold frequency. This is because the energy of the incident photons is insufficient to overcome the material's work function and eject any electrons. Scientists carried out an experiment comparing X-ray diffraction with electron diffraction by analyzing the patterns produced by passing an X-ray beam and an electron beam through a thin polycrystalline aluminium foil. The X-ray photon energy and the electron kinetic energy are the same. The patterns produced have the same general appearance, but different spacings. Given that X-rays have an energy of 137 eV and travel at the speed of light, their wavelength can be calculated using Planck's equation. Here, the unit of Planck's constant is electron volt second, not joule second, since the energy of light is represented as electron volt. Given the electron's kinetic energy is 137 eV, we can calculate its de Broglie wavelength. First, the energy must be converted from electron volts to joules. Next, using the classical kinetic energy equation, we find the electron's speed. Finally, the de Broglie equation is used to determine the electron's wavelength from its speed and mass. The mass of the electron is a fundamental constant found in a databook. Although X-rays and electrons have the same kinetic energy, they produce different diffraction patterns because their wavelengths are not the same. The wavelength for each is determined by its momentum. Since an X-ray is a massless photon and an electron is a massive particle, they have different momenta for the same kinetic energy, which leads to different wavelengths, and, therefore, different diffraction patterns. The sodium vapor lamp emits a characteristic yellow light, with a wavelength of 589 nanometers. The energy of a single photon can be calculated using Planck's equation. Since the energy is to be expressed in electron volts, eV, it is convenient to use Planck's constant in units of EVS. When an electron in a sodium atom transitions from a higher energy level to a lower one, it emits a photon. The energy of this photon is equal to the energy difference between the two levels. Since the emitted photon has an energy of 2.11 eV, the electron must have jumped down between two energy levels with a difference of 2.11 eV. This transition is visually represented by a downward pointing arrow on an energy level diagram. The ionization level for sodium is 5.14 eV. This means that an electron must absorb a minimum of 5.14 eV of energy from a photon to be completely removed, or ionized, from the atom. This transition is represented by an arrow pointing straight up from the ground state and extending past all the discrete energy levels to indicate the electron has escaped. The final state of the electron after ionization is considered to have zero kinetic energy, so any extra energy from the photon will be converted into kinetic energy of the freed electron. This section explores various aspects of the photoelectric effect and related phenomena. It covers 19 marks and contributes 14.7% of the total 130 marks. Multiple choice questions, 2 marks. Question 18 asks how the work function affects the kinetic energy of photoelectrons. Question 19 involves calculating the number of photons per second from a laser's power and wavelength. Short answer questions, 17 marks. Question 16 Photoelectric experiment focuses on calculating maximum kinetic energy and work function, and explaining how changing light intensity or frequency affects the results. Question 17. De Broglie waves requires calculating the wavelength of both X-rays and electrons and explaining why their diffraction patterns differ despite having the same kinetic energy. Question 18. Energy levels involves calculating the energy of a photon emitted by a sodium lamp and drawing the corresponding electron energy level transitions. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.